So maybe let me start. Are there any questions that anyone wants to raise? So if not, let me start by addressing a question which Ken asked last week or last lecture after the lecture. So which is maybe, so in the lecture, I talked about this low pair maximum principle, and I said, if we define x and t to be b of xt minus b of x naught t, and then if there's some x and t naught such that the derivative of f equals 0, where let me recall the context. So you had some point x0, and you had a curve of y's, y sub t, connecting y0 to y1, which such that this was a b segment with respect to x0, and then you find the t naught at which is quantity, and the x at which is quantity f has a critical point, and then you construct a b segment xs connecting x0 to x1 with respect to yt naught. So the b segments here are x0 yt, the map t goes to this, and the map s goes to xs yt naught. And so I said this, so of course this is, if we compute this, right, df by dt, sorry, and I didn't say what this is. This should have been y of t and y of t in both places. And if I compute this, then of course it's y dot of t naught. Let's say, okay, so here's a bit of notation that's convenient. So inner product with dxb at x yt naught minus dxb at x naught yt naught. And so sometimes people like to write these in coordinates. So if I wanted to write this in coordinates, it would be something like y dot I, and then it would be db by dxi. And so sometimes people write b sub I for that. And but this is at x yt naught minus x naught yt naught. And so my notation here is that if I have something like bi comma j, it means d2b by dxi dyj, and any other y derivatives I'd put after the comma, and any x derivatives I'd put before the comma. So I can write this difference between these b's at different points as an integral along the curve xs of oh, sorry, and again, so this comma, the I should come after the comma, according to the notational convention that I just proposed, because it's derivative with respect to y. So then I might have b j comma I xs yt naught, and then I'd have x dot j of s. And my claim was that somehow that the integrand here is independent of s, and maybe I should write partial derivative d by ds of bji xs yt naught. Maybe I'll put the y in as well. It doesn't hurt. yi dot t naught x dot j of s equals 0. And I claim that that came from the fact that this curve was a b segment. And Ken said, well, but what do you do about the there's going to be an x double dot term under this derivative. What do you do about the x double dot term? And I hummed and hawed a little bit, but I eventually realized that, oh, I don't need to hum and haw, because really I can also write this as the second derivative with respect to s of b comma I, that's the y derivative, y dot I t naught. Maybe I'll take the y I out here again. And I guess this is always evaluated at xs y t naught. And the fact that, so we already, so this is what I want to show. But the fact that this thing vanishes is exactly the condition for being a B segment, for XS to be a B segment with respect to YT naught, right? Because this is what's under here is as I ranges from 1 up to n, I already know that this y derivative of B XS YT naught second derivative with respect to S is 0, because that was the definition of a B segment. And if you, on the other hand, if you wanted to write out explicitly what that means in terms of all the tensor notation or whatever, then you could so in other words, the smart thing to do is to not let this S derivative act, it's to undo the action of the other S derivative. But if you wanted to, you could write out what it means in terms of tensor notation. And I guess it would look like, if I let the S derivative act, I would have BJKI. So there's an overall yi dot, and then there'd be an x dot j, x dot k, and then there'd also be the bji comma x double dot. So this is also the tensor notation condition for xs to be a B segment with respect to YT naught, but this is somehow a little bit simpler, at least for me to deal with. Any questions? Does that help, Ken? All right, great. Okay, so I promised today to talk about this theorem of Lopez. So let me remind you, so the theorem was that if A0 to A4 holds, and A3 strong, and some mapping G pushes forward mu plus to mu minus, where I have two probability measures, and I think it's enough that F plus is bounded above and F minus is bounded below. Then G is Holder with some particular exponent. So 1 over 4 dimension minus 1 locally in the interior. Actually, yeah, okay, in the interior of M plus to M minus. So that's the theorem I wanted to prove. And the proof relies on a proposition, and so let me try to say what the proposition is about. So the idea is that it's a dichotomy proposition that says either you're already Holder continuous. So if I have some x, a pair of x's, x0 and x1 that are close together, and that, oh, sorry, I didn't say be optimal. That are mapped to some corresponding pair of points, y0 and y1. So really what I mean is that xi and yi are in the B subdifferential of u, for u the self-dual object whose such that G is the b exponential composed with du. No, G isn't, well, okay, G isn't defined at every point. It's only defined almost everywhere because so far all we know is that U is a Lipschitz function or maybe semi-convex. So it's defined at most points, but maybe not everywhere. But just for simplicity of notation, instead of writing this, I'm going to write Y naught is G naught of X naught and Y1 is G of X1. So there are two situations. Either the Y naught and the Y1 are already close together, comparatively close together compared to X naught and X1, in which case everything's good. The mapping is a contraction or something, or at least continuous. Or the Y and the Y naught are far apart, which is what I tried to draw here. And then so that, so then the idea would be that on the line segment joining X naught to X1 is some point, which I'll call X2, the mid, somewhere between them. And the idea would be you can I construct the B segment YT joining Y naught to Y1 relative to X2. And then I look at the middle third of that B segment. So I take a neighborhood of radius delta around the middle third. And I take a ball of radius epsilon around X2. And because Y naught came from X naught and Y1 came from X1, everything in this delta neighborhood actually, if I choose delta and epsilon correctly, everything in this delta neighborhood had to come from this epsilon ball. And then, so you show that you try to derive a contradiction from that if you by choosing epsilon and delta correctly. And so let me try to quantify this proposition. So the proposition is that given xi, yi in b derivative of u for I 0, 1, and setting, I'm going to let delta x be the difference between x1 and x0, and delta y be the difference between y1 and y0. So either delta y is already small compared to delta x or not. So this is the not case. If delta x is small compared to the fifth power of delta y, that's the case in which I wouldn't already have that things are looking Holder 1/5. Then there's a ball. Yeah, sorry. There's a ball B epsilon around X2, which contains the preimage of this sausage or of radius delta around the middle third of that segment, where epsilon is going to be some constant to be chosen later. I guess we could call it C2 of square root of delta x over delta y. X2 is in the line segment joining X0 to X1. And S delta is the set of all y in the target, which are and here delta is another constant, let's say C1, I guess, epsilon delta y squared, and yt is a b segment as I described. So in other words, 0 is the second t derivative of dxb x2 yt. That's the B segment condition. And I'm going to probably drop the constant. So I'll just say this is proportional to epsilon delta y squared. And this is proportional to delta x over delta y. But I can choose these constants C1 and C2 later in the proof at whenever, give them whatever values are convenient. Okay, so that's the story. And that's the proposition. The proposition is sort of technical, and I will come back to it, but let me at least show that if the proposition is true, so that I can find these points that I've described, x2 and so on. If under this hypothesis, whenever this hypothesis is true, then I can find an x2 and epsilon of the size I described and delta of the size I described for some C1 and C2, such that we call this, Young-Han and I called this the sausage into ball lemma, because it's sort of a sausage around this middle. It's a sausage over here around this ball around x2. And somehow the idea is there's too much volume in the sausage, so that's going to violate the fact that G is supposed to be a measure preserving map between F plus and F minus. So let me try to do the proof of the theorem given the proposition. Taking the proposition for granted. So the points where whenever the opposite inequality holds, we're already, whenever this is bigger than or dominates delta y, we're in good shape. And if not, apply the proposition. So if you can find a pair of points x1, x0, and x1, and the corresponding points y0 and y1, which violate this inequality, apply the proposition to get x2 delta and epsilon, such that this ball contains the pre-image under G of the sausage, or you could also write something like the whatever. There'd be a non-smooth notation for this as well. I guess it's like the B tilde subdifferential of U B tilde of the sausage. Anyhow, and so you want to integrate F plus over this. So what does this say? This says integral of F plus over the ball of radius epsilon around x2 would have to dominate integral of integral d mu plus of G inverse of the sausage. But since mu minus is mu plus pushed forward through G, this is like the integral of mu minus over the sausage itself. And so apart from dimensional constants, this is something like, so apart from constants, this is something like the L infinity norm of F plus times delta to the nth power. Now this sausage has some length, so it's going to be more like delta to the n minus 1th power. So this is going to be bigger than something like, neglecting the dimensional constants, this is going to be bigger than something like the distance, 1/3 of the distance between x0 and y0 times delta to the n minus 1 times the lower bound on F minus. And so I'm going to, assuming that F plus has an upper bound, F minus has a lower bound, let me forget about them. So what do I have? I have epsilon to the n is up to constants is bigger than delta y, delta to the n minus 1. And now I need to remember how my epsilon and delta were chosen. So epsilon up to constants was square root of delta x over delta y. And delta was, apart from constants, epsilon times delta y squared. And maybe it's best to square everything. So let me make this 2n and delta squared and 2n minus 2. So now on the left, I have delta x over delta y to the n is controlled by constant times delta y squared. Oh gosh, maybe I should wait. I could have done this in a little simpler way, but okay. So the epsilon, yeah, I should do it in a simpler way. So this is delta y squared, epsilon to the 2n minus 2 delta y to the, I guess 4n minus 4. And so I should cancel a bunch of powers of epsilon first. So before I do this, I should cancel. I guess I'll just be left with 2 powers of epsilon if I cancel all of these. So which says delta x over delta y dominates delta y squared. And what am I left with? Plus 4n minus 4. So that sounds like if I can cancel 2 and make this minus 2. And great. So now I'm home free. So finally, delta x up to all these constants dominates delta y to the 4n minus 1. And that was what we claimed. That's the Holder 1 over 4n minus 1 estimate. Where the constants in this inequality depend on the lower bound for f minus, the upper bound for f plus, the constant c1 and c2, and also, yeah, the constant c1 and c2. Is that part clear? Any questions? So that's the proof of the theorem given the proposition. Proof of the proposition is a little bit more involved. So let's see, here's the proposition. This is basically from my notes with Guillen. So the proposition starts with 2 points which correspond to each other under the map G, and it assumes that the delta y's are far apart relative to delta x's, and it asserts the existence of the epsilon of this form and the delta of that form, such that this sausage over here has its preimage inside this ball over here, and that the x2 is on the line segment joining x0 to x1. So let me talk about how this why this proposition is true. And also, I guess, let me also remind that basically what is this theorem saying? It's a continuity theorem about optimal maps. So it's saying that if you're mapping lines to factories, it's saying that when the result of the theorem is true, the factory supplied is going to depend continuously on the mind supplying it with some Holder exponent 1 over 4 minus dimension minus 4 times dimension minus 1. Or if you're pairing workers with firms in a matching setting, it's telling you the firm the worker is going to work with is going to be a Holder continuous function of the identity of the worker. Okay, so let me come back to the proof of the proposition, and I'll try to draw a better picture. So the idea is I have this x0 and x1, and I have this B convex function u, which maybe looks like this. And the slopes sitting above this function above x0 and x1 are going to be very different, because the x1 so if delta x is small compared to delta y to the 5th, then the slopes here and here have to be quite different, because the y0 and the y1 are quite far apart. But nevertheless, you have these supporting B functions, which touch U here. So that'd be like B of X minus X at Y1 minus constant. And you'd also have a choice of Y, namely Y naught, such that the B function touches U here. And U is, you can always add a constant to U, provided you subtract the same constant from V and you don't change the dual problem at all. So I can always shift U up and down by a constant if you like. And it's convenient in this proof to shift U up and down by a constant so that the value where these two B's cross is 0. And of course, the set where the B at Y naught minus lambda naught is beneath the B at Y1 minus lambda 1 is it's like a half space, maybe with a slightly curved boundary because these functions are not quite linear. And so there's a half space with a quite slightly curved boundary cutting through here somewhere. And of course, X naught has to be on one side of that half space and X1 has to be on the other side. So take the line segment joining X naught to X1. This half space that I tried to draw is the set where B Y naught minus lambda naught equals B Y1 minus lambda 1. And choose X2 to be the place where on the boundary on the frontier between the region where one of these things is less than the other. So maybe if I wrote it like this, then I'd have a region like that, and I choose X2 to be in the boundary of the region. Border or boundary or whatever, frontier. And actually, sorry, I was vague. So the value where these things intersect is different at different points. Choose X2 to be on the boundary where they intersect, and then slide the whole picture up and down so that the value of this intersection at X2 is 0. That's better. And so I need some names for these functions. So I'm going to let F, so this will be the function F0 of X, and this is going to be the function F1 of X, i.e. Fi of X is B of X, yi. And then if you think, what does the constant have to be? It has to be minus B of xi, yi, plus something, plus u at xi. That says that this function goes through this point for when I is 0, and when I equals 1, it says it goes through this point over here. And we have and F0 of X2 equals F1 of X2, and I've normalized that to be 0 by shifting the whole picture up and down by constants. And so the first fact is that U is semi-convex because it's a supremum of smooth functions B. And that tells me something. It tells me that the value here of U at X2 can't be too big relative to 0. So I claim that U of X2 is no bigger than, up to constants that I want to write down, is no bigger than delta x delta y plus some large constant times delta x squared, the constant of semi-convexity times delta x squared. And this actually basically comes from the smoothness of B. let's see. Do I believe that? So it should come from Taylor expansion of U or of V or of F. Right, so I guess Fi at any point is bigger than or less than. Okay, maybe I should pause that for a second. Okay, let me come back. Let me take this on faith for a minute. So semi-convexity of U is supposed to give me this estimate here. Let me think again where that can come from. So I want to say f of n, if I get a lower bound for f, it gives me a lower bound for u, but that's no good. So I need an upper bound for f, right? So fi of x is less than, let's say, fi of xi plus derivative of fi at xi, x minus xi, plus a correction, which is something like the C2 norm of fi times x minus xi squared. Good. And let me see if I do that. No, the problem is that fi is a lower bound. So what I'm bothered by is how to turn this into an upper bound for u at, what am I wanting, a lower bound or an upper bound? I'm wanting an upper bound for u. Okay, I should leave that one alone for a bit. Let me see if I can proceed with the proof. Let's take this bound on faith and I'll proceed with the proof. I mean, I can sort of say what the idea behind this bound is. And so the idea behind this bound is it has the flavor of what I'm writing down, except this is the dfi of xi is sort of like du at xi because they have the same slope. And so that's somehow related. And then this x minus xi, if I evaluate this at x2, that's going to be a fraction of, it's going to be either t or 1 minus t times delta x, depending on whether I is 0 or 1. In fact, there's an equality here. And so this is going to be either t or 1 minus t. And somehow I'm going to sort of add these two things together, but noticing that x2 minus x0 and x2 minus x1 have opposite signs. And when I add these two things together, something is, the leading order term is going to cancel, and what's going to be left over is this term, which now is going to involve basically the difference between the du's is going to be like delta y, and it's going to be times delta x, and that's where this delta x times delta y comes from. And now the only thing that's bothering me is that maybe I'm supposed to have written this, I'm supposed to have done the Taylor expansion around x2 instead of doing it around xi, but that's a little fishy. So this is basically a Taylor expansion argument, and the constant is controlled by the smoothness of B. This is the smoothness of B in here that's controlling this. Okay, so semi-convexity of U is supposed to give me this inequality here. And then I'm going to somehow want to apply, yes, so now I need to, the other ingredient in this proof is that when you have A3 strong and you have B segments XS and YT, and you compute the fourth derivative of B at XS and YT, when the second mixed partials vanish, then we said the fourth derivative had to be positive, but in fact it had to be larger than this. The strong part here says that in compact spaces this is going to be larger than some constant times, I guess, delta x squared, delta y squared. And at least one of the curves is a B segment. One curve is a B segment. And so I mentioned this when we were proving Lopez's maximum principle in the last class, that you can quantify the positivity of this fourth mixed partial. But okay, so now I want to somehow apply this, and I want to apply it to the B segment. The only B segment in the proposition, let's go back, it's the B segment. This is the B segment here that I want to apply it along. So in other words, I construct a B segment of Y's relative to X2. So I'm rotating F0 into F1, and I'm rotating it through X2. So what I've drawn here is supposed to be B, YT minus whatever constant I need in order so that BXYT minus lambda 3 is 0 at X2. And as t goes from 0 to 1, it rotates this curve to that curve. And of course, so the value of this thing at X2 is going to be 0 because that's how I've set it up. But if I go a certain distance from X2, so if I go a radius epsilon out from X2, then I have some quantitative estimate of how far this black curve is beneath these two red curves. And so that's why I'm going to need to choose my epsilon to be whatever it was, delta x, square root of delta x over delta y, and look on the ball at that radius. So so this tells me that my ft, if I now define ft in analogy with f0 and f1, but now it's hinged at x2 plus, I guess, 0. That's my ft. Now I've done something a little bit funny here. So of course the ft lies under u. It lies under the f0 and f1. It also lies under the u. And oh yes, I've added u of x2 here, but u of x2 is 0, so that's irrelevant. So ft blah blah blah. No, yeah. This lies under the maximum, so it lies under u of x. So it satisfies ftx prime minus u of x prime. I'd like an upper bound for this. And sorry, so this is going to be is less than minus this constant times x prime minus x2. Right, it's not, what goes here is not x1 minus x0, because what matters here is that I'm choosing x prime to be a distance epsilon from x2. And so the change here is x prime minus x2, where this is the constant C3 from A3. Right, that's basically it. So up to, so again, there's some constant here. And so because I have this estimate, so of course, when x prime equals x2, that doesn't tell me anything. But when x prime is a distance epsilon from x2, it does tell me something. It tells me that I have some freedom for x prime not equal x2. It gives freedom to move y away from the middle third of yt a little bit. So right, and how much is the little? The little is going to be delta, and the distance between x prime and x2 is going to be epsilon in this sequence of estimates. Without spoiling, so I can move y a little bit without spoiling the following inequality. That if I now define g of y to be b of whatever y minus b of x2y, plus u at x2, which is always 0, that this is going to be less than u at some other point. So I know this is true along the segment. I know it's true along the middle third by Lopez's maximum principle. And by quantifying Lopez's maximum principle, I also know it's true in a neighborhood of the segment. So I could put the x if I wanted here. And then the question is, how far can you go? And the claim is that I can choose epsilon and delta, as I did in the proposition, and still have this inequality. And oh shoot, no, I'm wrong. This isn't 0. U at x2 is not 0. U at x2 is this little bit above 0, but I said it wasn't too much above 0 by the semi-convexity estimate that I quoted number 1. And so somehow the idea here is to check on the boundary of this ball that I can bump this thing up. I can bump this thing up a little bit and then tilt it a little bit too. So I can bump this thing up a little bit, and then I can tilt it a little bit by moving y a little bit away from y2, but it still stays underneath u on the boundary of this ball. And that means that u minus this thing, this gyx, is positive on the boundary of the ball. And gosh, oh yeah, sorry, I added u to it. So yeah, this was the funny thing that I did. First I kicked it up, so it was passing through this point, and then I twisted it a little bit. And so I know it doesn't stay larger than u everywhere, because I know it passes through u at this point, but I've twisted a little bit so I know that it stays underneath u at the boundary of this ball. And then that means that u minus this function has a minimum somewhere in the interior of the ball. And that means that the condition for u minus this function g to have a minimum is exactly the condition for x to be the preimage of y under g. And so that's telling you that all these points y in this sausage actually came from some point in the ball, and that gives us the contradiction we saw before. And so I guess what we still want to do is to see that we chose epsilon and delta correctly. And i.e. i.e. Okay, so let's see. Sorry, this is not going as smoothly as I wanted it to go, but so basically at this amount of space, so and then I add to this the offset that I had to do to bump this up to make it go through here. And that offset is controlled by the thing that came in the semi-concavity estimate, this. And so we have minus C3 x prime minus x2 squared delta y squared. And then we bumped it up by something that was no bigger than delta x delta y plus delta x squared. And we liked, I mean, sorry, there's constants in front of here, but never mind. And what we like is for all these offsets to add up to something negative. And so what's the idea? The idea is that if x prime minus x is epsilon, which is square root of delta x over delta y, and delta, where did delta come into it? Oh yes, sorry, so I've missed where delta came into this. So where delta comes into it is that I need to replace, if I'm going to move the y away from here, I need to replace a term like this with a term like b of xy minus b of x2 yt. And so the difference between this black term and this red term is basically something like, x2y rather. The difference between the black term and red term is the y has changed by an amount delta because there's some t between 1/3 and 2/3, which is delta away from y, and x has changed like the distance between x and x2, which for x, when x prime is on the boundary of the circled radius epsilon, is like epsilon. So I guess there's a term delta epsilon in here as well. So there's a term delta epsilon in here as well, and I want to control all these things. And so let's see if it worked or not. So we said the delta was going to be like epsilon delta y squared times a constant, but the constants are going to be irrelevant. So all of this stuff is going to be like epsilon delta y squared times the epsilon, and the epsilon is delta x over root delta y. This already doesn't look so good to me. Minus C3 x, so this is the epsilon again, epsilon squared delta y squared, that looks good. This delta x delta y, that's fine. And this delta x squared is okay. And I'm also helped by, sorry, I'll get rid of this epsilon now. This epsilon squared is like delta x squared over delta y squared. So I guess, so, oh no, it's like delta x over delta y, good. So this term here, so the minus C3 term has the flavor of being delta x times delta y. And this is the term that's kind of causing me trouble.
Should you have killed that epsilon? Because if you don't kill the epsilon, then it should become like something like delta x times delta y, right?
Maybe you're right. Yeah, good. Maybe I shouldn't have killed the epsilon. Thank you. Right, so it's this epsilon times delta gives me an epsilon squared. Great. So this is a term like delta x over delta y. Great. Right. And okay, so great. So there's so the point is that these terms are all of the same order as this term. And by choosing, but I had these freedom to choose the constants C1 and C2 that went into the definition of delta epsilon. And so I can make this dangerous term smaller than the C3 that comes out of my A3 condition. And so I can make that negative. And the delta x squared is no danger because I already have assumed that delta x was small compared to delta y to the fifth. So this delta x squared term over here is no danger at all. I'm slightly bothered about this term, but I think that I probably shouldn't spend more time on it. But thanks, Cameron, for saving me. Right, so I did, there was this crucial estimate that I got, bxy minus bx prime y minus bx2y, difference b x prime yt plus bx2 yt, and that this is going to be like of size epsilon delta. And that was where this term came from. And then I also I apologize that I didn't that I'm not able to give you the detailed proof for this semi-convexity estimate right now. I mean, you can kind of see it that if u was too big, then the function would have to be very concave, and you know it's not, because semi-convexity prevents it from being too concave. And then it's just a question of quantifying how big can you be, and it's clear why the delta x comes into it, because this whole interval is of length delta x. And the reason that delta y comes into it is basically delta y is measuring the distance between these two slopes. But that the fact that you chose x2 to lie on the line segment joining x1, x0 to x1 is exactly what tells you that you get these two canceling contributions in the Taylor expansion. So that's my impressionistic proof. And I guess if you want to see this, so somehow in our 2010 paper, Young-Han and I wrote this proof in great detail in an appendix, but the referees didn't like the appendices, so they cut it from the paper. But if you go back and look on the archive version, in version 1, you can find and I think we cite that in the paper with Gian, you can find the proof in glorious detail. But let me do something more, maybe more interesting, which is to try to give some intuition behind what's really going on with these conditions A0 to A4. Maybe before I do that, I should stop and ask, are there questions? Are there questions about my impressionistic proof? Okay. So let me give try to give a little bit of intuition on A0 to A4. And I like to do this using a function that I call a cross difference. But so let's say a subset of m plus cross m minus is B. We know what it means to be cyclically monotone, and of course B monotone just means for every x0, y0, and xy in S, for every pair of points, that the following function delta xy, x0, y0, which is given as bxy plus bx naught y naught minus what I get if I change partners, is bigger than 0. And sometimes I'm going to want to regard x naught and y naught as being fixed and xy as being variable. So I mean, I guess that it's really a pair of points in S that I'm choosing. And what do I want to observe about this? I want to observe, let's Taylor expand around x naught, y naught. Well, actually, even before I do that, let me make a remark, which I think I'm going to put on a problem set. Obviously, x naught, y naught, so d delta naught with respect to xy, evaluated x naught, y naught vanishes. And A3, or A1 rather, A1 holds if and only if delta xy has no other critical points. Save x naught, y naught. So this should hold true for every x naught and y naught, that delta has no other critical points. Delta naught has no other critical points. Okay, so that's a nice remark. That explains condition A1 a little bit. But now let me Taylor expand delta naught around x naught, y naught. So delta naught of x naught plus delta x, y naught plus delta y. Well, of course, if I plug x naught, y naught in for x naught, y naught, I get 0. So the first order in the Taylor expansion vanishes. And by this remark, the second order term in the Taylor expansion vanishes as well. And so the first non-zero term is going to be the second order term in the Taylor expansion, which is something like delta x, delta y, h naught, delta x, delta y, where h naught is the Hessian at x naught, y naught of delta naught. And then there'll be, as long as b is a smooth function, then the next correction to this is going to be delta x, delta y cubed term. As delta x and delta y go to 0. And the Hessian of this function is, if I think about the Hessian of x naught, of delta naught rather, if I take two x derivatives and set x naught equal to y naught, the contribution from this term, the x derivatives here, and this contribution from the x derivatives here is going to exactly cancel each other. So in principle, this thing looks like a big matrix with, the double x derivatives of delta naught and the double y derivatives of delta naught, and then the mixed derivatives of delta naught and their conjugate. These are all second derivatives. But what I just argued was actually this term is 0. And similarly, if I take two y derivatives, there's a y here and there's a y here. But if I take the same y derivatives of both of those terms and then set x naught equal to y naught, they're going to cancel each other. So this term is 0. And so in principle, I have this 2n by 2n matrix if the manifolds m plus and m minus are m dimensional, but they have 0 n by n blocks on the diagonal portions, and it's just the off diagonal portions that are non-zero. And so that tells me that that this in this Taylor expansion, the leading order term has a very special form. It's basically something like the delta x here never sees the delta x over there. It only sees the delta y over here. And similarly, the delta y never sees the delta y. It only sees the delta x. And so it's something like the double sum on I and j of delta xi, delta yj, mixed derivatives of b with respect to xi, yj. Plus these lower order terms. And because of the structure of the matrix, what I see is that neglecting the lower order terms, if I change one of the signs, let me change this plus to a minus, then that's going to be equal to delta naught x plus delta x y naught plus delta y naught plus lower order terms up to a, sorry, the sign change is going to change the sign here. Right, because if I only change the sign on delta y and I don't change the sign on delta x, I change the sign of one thing here, but not the other guy. And so that means that the symmetric matrix H naught's a symmetric matrix because it's a Hessian. So its eigenvalues, it should all be real. And because of this property, that when I change delta y, I change the sign, they come in plus minus pairs. And by the way, condition A2, rather, asserts the determinant of H naught is non-zero. And so somehow the idea is I can regard this H naught as being a little bit like a metric tensor. After all, it's non-degenerate for each source and sink pair, for each source and target pair. But it's not a positive definite metric tensor because the eigenvalues come in plus and minus pairs. It's some other kind of metric tensor. It's non-degenerate, but not positive definite. So it's not a Riemannian metric. It's what I guess is called a pseudo-Riemannian metric, or sometimes semi-Riemannian. Its signature is, it has the same number of positive and negative eigenvalues. So it's signature NN on this 2n manifold. So it's either pseudo or semi-Riemannian. So the picture is you have the product space M plus cross M minus. And you have this sort of non-degenerate metric tensor on it. And those of you that did the first question on the first assignment wrote down in the Riemannian context what the geodesic equation looks like in local coordinates for an arbitrary positive definite metric tensor. But the formula you wrote down, Riemannian geodesic equation, it looks in the formula is something like x double dot plus some gamma I j k x dot j x dot k, where gamma I j k was basically something involving derivatives of the metric tensor. So something like dg, so there's an L that comes into it. Lk dxj plus dg jl dxk minus dgjk dxl, and then multiplied by the inverse, so GLI, the inverse, this is the inverse matrix to the lower G. This formula makes, and I don't remember if it's plus or minus, I may have it wrong up to a plus or minus, but this formula makes perfectly good sense whether the matrix, all you need is invertibility of the matrix G, right? This is GLI inverse as a matrix, not as a component. all you need is invertibility. So this formula for geodesics makes perfectly good sense whether the matrix G is positive definite or not. And these B segments that I've been talking about, so here's another nice fact. B segments x naught yt and xs y naught solve the geodesic equation, the same geodesic, the analogous geodesic equation for the metric H on m plus cross m minus. And you can kind of, if you just look at the form of the equation, right, it's linear in the second derivative term and it's a product of first derivatives. And if we go way back to the beginning of my lecture where I answered Ken's question, you can kind of see that happening already here, that the condition for a B segment was sort of linear in the second derivatives and quadratic in the first derivatives along the curve. And then it had these coefficients. And the coefficients are basically the gammas. Okay, you know, I just need to get the term off this, I need to multiply by the inverse of this matrix, which is assumed to be invertible in A2. And the condition A4, it says if you pick a point here and you look at this entire fiber, x naught cross m minus, or if you pick a point over here and you look at this entire fiber, m plus cross y naught, it asks for these two things to be are geodesically convex for H. In other words, it says whenever I have a point here and here, you should be able to find a curve that lies entirely in this fiber that joins this point to that point, which is a geodesic with respect to this not necessarily positive definite metric H. In fact, non-positive definite metric H. And so that leaves us with A3, right? What is A3? And to understand A3, it's nice to go back to this Taylor expansion of delta. So far, I only carried it out to order 3. But let's change tactics a little bit, and let's Taylor expand delta naught around a curve xs yt, where which happens such that so let s, let's say minus 1, 1 going to xs y naught, and t also minus 1, 1 going to x0 yt be B segments. And now let's Taylor expand delta naught, taking set x naught y naught to be x0 y0, and let's Taylor expand delta naught xs yt. And of course, the first term is, we already saw, is going to be something like 1/2 x dot 0 y dot 0 h naught x dot 0 y dot 0. And that'll be multiplied by s. Oh, sorry. Yeah, that's fine. And I guess there'll be an s here and a t there, and an s here and a t there. But maybe it's s plus t cubed, absolute s plus absolute t cubed, whatever. because of the special structure of H naught, you can also pull the ST out because only one, that we argued that already. Only one X term and one Y term contributes. And now I'd like to go to higher order in this Taylor expansion. So let me call this maybe the 1,1 term, constant C11. And then I'd have terms, at the next order, I might in principle have something like C30 S cubed plus C21 S squared T plus C12 ST squared plus C03 T cubed. But in fact, most of these terms vanish. In fact, all of these terms vanish. So I claim all these constants are 0. And how do I see that? Well, delta, let's see, delta 0 of XS Y0, by definition, that's B of XS Y0 plus B of X0 Y0 minus B of X0 Y0 minus B of XS Y0. So it's identically 0. So that tells me that anytime I have pure S derivatives, so let me call this function f of S and T. So this tells me that I can take KS derivatives of f, and if I evaluated S0, and that's identically 0. And similarly, I could take KT derivatives of F0T, and that would be identically 0. So far I've shown that this term vanishes and this term vanishes. And similarly at the fourth order, the S fourth term, the T fourth term also vanish. So far the Taylor expansion so far of FST is C11 ST plus, now I can go right to the fourth order term. There's like C31, there's C21 S squared T plus C12 ST squared plus C31 S cubed T plus C22 S squared T squared plus C13 ST cubed. And so next I want to claim that because I chose these two curves to be B segments, this term and this term also vanish, and so do this term and that term. Plus order S plus absolute T to the fifth power. And so let me try to argue that. Maybe it should be plausible, but so let me try to argue that these four terms have to disappear as well. So what was f of st again? It was like b of xs, yt, and then there were terms, well, I'll write them down. But if I'm going to take mixed derivatives like two S derivatives and one T derivative, then that's going to kill this term. There's no T derivatives, there's no T dependency here. It's going to kill this term and it's going to kill that term because there's no S dependence here. So I might as well just be taking derivatives of this. And so let me take a derivative. So let me take a derivative of that with respect to S, say. And then maybe set S equals 0. So what am I going to get? I'm going to get the x derivative of b at x0 yt times x dot of 0 And then no matter how many t derivatives I take, the first two, because the equation for this thing to be a B segment says that two t derivatives of this vanish. So as soon as k is bigger than or equal to 2, this is equal to 0. Because xt, yt is a B segment. Right, so that tells me that indeed this term vanishes and that term vanishes, and in Pascal's triangle this term would vanish and so on. And the same argument from the S side instead of the C side tells me this term vanishes and that term vanishes. And so then this is the up to order 4, up to order 5, there are only 2 non-zero terms. This one that we've already seen and this guy here. And well, what's C22? Well, Taylor's theorem, therefore f of st, Taylor's theorem basically tells us what these coefficients are, right? It's the mixed second derivative of s with respect to s and t at 0, 0 times st plus the mixed fourth derivative of s with respect to s squared t squared at 0, 0, st equals 0, 0. Yeah, times s squared t squared, and I guess there's probably a factor 1/4 here, plus terms of order s plus t to the 5th. And so this is exactly the quantity that appeared in A3. And this is supposed to remind you very much, if I oh yeah, right. Great. Let's go back to Riemannian geometry for a moment. On, let's say, an n-dimensional manifold G with a metric tensor Gij. So on the first assignment, you saw the geodesic equations. So let x of s, let s goes to x of s, and t goes to y of t, be Riemannian geodesic. So now I forget about everything I just did. I'm now in the context of a traditional Riemannian manifold, which means they're locally, if you know a little bit of Riemannian geometry, you know that these are locally at length minimizing. So you also saw the definition of the distance, the Riemannian distance, and the Riemannian distance squared. And so, and then Taylor expand Riemannian geodesics through a common point. And let's say arc length parametrized. It doesn't really matter. Maybe it's convenient, maybe it's not convenient. So the picture is I have two curves, x of s and y of t, x of s and y of t, such that when s equals t equals 0, they pass through the same point. And then the question is, what's the Riemannian distance squared between those curves? How does it depend on s and t? And if you do the kind of calculation we just did, you'll find that, of course, there's it's the leading order term is going to be something like s x dot 0 minus t y dot 0 squared in the Riemannian metric. Those are tangent vectors. And if you take t to be 0, then this curve here is going to be exactly the distance from xs to y0 is going to scale exactly like s squared times the arc length parameterization. And so there'll be no higher order corrections in s. There'll be no pure power s cubed or pure power s fourth, just like we saw above. And because these are geodesics, there's going to be no single power s times the power of t either, or single power of t times a high power of s. And so the next non-trivial correction to this is minus, again, a constant times s squared t squared. Let me call it c, I guess I'll call it c prime 2 or whatever, plus order s plus t to the 5th. And this constant, of course, C22 prime, in principle, it might depend on, it certainly, you can expect it to depend on x, the tangent vectors x dot and y dot. And you might also think it's going to depend on something like x double dot and y double dot. But from the geodesic equation, you can rewrite the x double dot term as a product of two x dot terms. And you can rewrite the y double dot term as a product of two y dot terms. So in fact, it only depends on x dot and y dot. But it depends quadratically on both of them. So it turns out that so the fact is that C22 prime, it has four arguments. I don't know, let's call it P, Q, R, and S, is multilinear in P, Q, R, and S, where P equals x dot equals R and Q equals y dot equals S. And well, now you can guess what it is probably. It's called the C22 prime is called Riemann's curvature tensor. And so, well, maybe I should say C22 prime is R of this, where R is a multilinear object and its variables. And so let's say R is called the Riemann curvature tensor, and C22 prime, which is R of x0 dot, y0 dot, x0 dot, y0 dot, is up to a constant, and I don't remember what the constant is. Just so here the constant was 4. I think here the constant maybe 3/2 or something, or 3/2 times 4, or 3/2 divided by 4 or something. So it's up to, it's a constant times what's called, so this, yeah, is, so the constant's already here, is a constant times what's called the sectional curvature of the two-plane x dot wedge y dot. So in other words, if we were in an n, I had this picture, but if we were, here was the picture. If we were in an n-dimensional manifold, the two tangent vectors to this, to these two curves would pick out a two-dimensional subspace of that manifold. Associated to that subspace is a number, and aside from normalization, that number is the sectional curvature. I guess if you want the normalization, then you really want to take these to be arc length parametrized. And so this object that we computed from the cross difference is the Riemannian sectional curvature of the pseudo-Riemannian curvature tensor H. And so really what A3 is asking is that certain sectional curvatures is that when you take these two, we go back to the picture, when I take a horizontal vector here, one parallel to m plus, and a vertical vector parallel to m minus, if the C11 term vanishes, which is, say, if these two guys are orthogonal with respect to the metric H, then the sectional curvature of the associated two-dimensional space is non-negative. So it's really a curvature condition. And maybe it's a surprise to see, well, certainly it was a surprise to discover that pseudo-Riemannian geometry was in this problem, but maybe we shouldn't be so surprised, because if we do optimal transportation in a setting of manifolds, and if the optimal map's continuous, then it shouldn't matter what coordinates you use to parameterize the two manifolds. It's going to be continuous between any pair of coordinate systems. And so somehow, if you have a necessary and sufficient criterion for continuity of the map, then that criterion has to be independent of what coordinates you use. And the quantities that are independent of coordinate systems are geometric quantities like curvatures. Okay, so that's, I think, a good place to stop. Anyone want to ask a question on the record before I turn the recording off? If not, we'll segue to office hours.